All right, let's go ahead and get started. About to start section 2.8. This will wrap up chapter 2. Anybody have any questions before we get going? All right, let's go for it. So, I asked this a few times, but just remind ourselves, what does it mean for a function to be differentiable at a point? Sorry, what was that? So that's one thing we've said, right? The derivative exists at that point. Anything else we've said about this? So the derivative exists at the point. So that's kind of like baked into a function being differentiable. It will also be continuous. The derivative exists at that point. So if the derivative exists there, what's the derivative tell us about a function at the one specific point that I care about? So those are the two big kind of representations of it, right? So the slope of a tangent line or the slope of the curve itself, both the same thing. The instantaneous rate of change. But if the derivative exists, then those things exist at that point. That's the big thing I want to make sure we pay attention to. So basically the derivative exists and we kind of know how to conceive of a derivative. So one thing I want to show you is this. So can you see this graph here? So basically what I'm doing is, so in red, you see the graph of y equals 1 over radical x. So then what's going on in blue then?
That's like the tangent line to that point.
Yeah, it's the tangent line at that point that are given. So the point of 1/4 and comma 2. So what does that line in that curve have in common? The slope and a point. Is that slope going to be true of that function anywhere else? No. So it's only that one point though, right? So, but at that point, I do know that I know something about the slope of the tangent line, and I have that one location, that point. What do you think is going to happen if I zoom in really close on that point A?
Like really close to touching and not have to touch.
I mean, do they touch?
At that point.
At that point they do, right? So why are they getting, like, they're starting to fade into each other, right? Why is that happening?
Getting infinitely close but not actually intersecting.
Right. So remember, I'm getting right now. I can get as close as I want, or until Desmos tells me I can't zoom in anymore. But let's just say for now I can get as close as I want to that point. But think about what a derivative means. A derivative really is a limit, right? Which means I can get as close as I want to that point, and the slope will basically approximate the curve, except the point. The point has the exact same slope. But basically, what we're going to be resting on for the first part of class today is the fact that the derivative, basically the tangent line, is very, very close to the curve if you get close enough, right? Are we okay with that rationale? I mean, that doesn't really make any sense if I do this. Now they absolutely look nothing alike, but you know, if you're in this little tight neighborhood around a point of interest, then you can say the tangent line and the function itself are very closely related. So from that idea comes this idea of local linearization. So I can use derivatives to approximate a function around a certain point like a straight line. And notice this equal sign here. I'm not promising equality for any x once you've left the point that I care about. I'm giving you some approximation to some degree of error. So any questions about the rationale We have complaints about the fact that we're going to use a straight line to stand in for something nonlinear. All right, so let's take a look at this idea with a couple examples. So I want to linearize this function, f of x equals 1 plus sine of x at this point 0, 1. So off in the margin here is the function 1 plus sine of x linear. It looks something like that, right? Clearly, deeply nonlinear. But I want to approximate this function at where x equals 0. So I'm going to have a tangent line that kind of looks like this, right? So that should tell you a little something about, if this is at all accurate, hopefully we have some kind of idea about what this tangent line is going to look like, right? So basically what I'm doing here is, and I know a lot of you just kind of wrote down the equations that I gave you, but essentially what you're doing is you're finding the equation of a tangent line to some curve around some point. So let's think of it that way. Can I find a tangent line of that function at that point? What do I do to get started there? Okay, let's find the derivative. What is the derivative of f? Cosine x? Okay. So the derivative is cosine x. And I only care about it at a certain place. Where is that? 0. So f prime of 0 equals cosine of 0, which is equal to 1. So I have my slope. Is that enough? Is it okay if I just say that my equation of my line is y equals x plus 1? How did I get there so fast? Gave you the y-intercept, right? So got the slope. Y-intercept was given if you recognized it, but there's my equation of my line, right? Y equals x plus 1. Clearly, if you look at the graph up there, there's a very small window where that even comes close to making sense, right? If I put in 5 for x, this is going to be nonsense. But I'm not going to use it for that. I'm looking for it around, fairly close. So I want to use this to approximate f of 0.1. So if I use this linearization, then I can say f of 0.1 is approximately equal to what? 1.1, right? So that's what f of 0.1 is approximately equal to based on the linearization that we did. Now, what if I want to find that exactly? Or more accurately? You can't really do it exactly. Anyone know what the sine of 0.1 radians is off the top of their head? No. Why would you? So that's part of why this approximation thing is done. I'm substituting some function that I don't really have a good idea of how it behaves unless I'm at like these very specific points. And I'm substituting that for some very easy to understand thing. So what is the sine of 0.1 plus 1? It's not that different. 1.0998. So as long as I stick to an area close to my point of interest, my base point, the approximations should be pretty faithful. Any questions there? Tom?
So all you did to get f of 0.1, you just plug it into the
So let's talk, so, I said f of 0.1 is two different things, kind of, right? Not really. Where did I get this number from? This is from a tangent line, right? Okay. And we know what this notation means?
Yeah, it's like
Okay.
approximately.
So remember, by definition, to start here, I said f is this sine function, right?
Yeah.
So I can't use this tangent line to say things about f exactly. I can only use it to make guesses that have error baked into them somehow. So let me make it clear in the notes here. This one comes from the linear approximation. And this one comes from, definition of f. And just to be clear, what is f of 2 approximately? 3? If you know how the sine function behaves, you'll know that 1 plus sine of x will never reach 3. But I'm just doing this to give you an extreme example of why this falls apart quickly. What is the sine of 2 radians? 0.909, so this is going to be 1.9093. So that's a real bad approximation. So approximations are useful for, for some area, some region, but not everywhere.
So the linear approximation is plugged into the tangent line, and there's a
Yeah.
definition of f is plugged into the actual function.
Yeah, and I'll answer it this way. This word linear is not, this is chosen carefully. This comes from this straight line thing that we've done. Any other questions about this? All right. I want to use the linearization of this function to approximate radical 16.5. So I'm giving you the function that I want to linearize. I didn't really tell you a point around which to linearize. But what's like a good base value? Like we'll call it A. Remember, when you take a linearization, you're approximating around one single point. So basically, what's my single x value that I'm going to base this approximation on? 16.5 would be exact, right?
Could you use 4?
I know what you're getting at, but it's not going to be 4. Why'd you think 4?
The square root of 16.
So it's the square root of 16 so 16 is the input to the function, right? So I'm going to approximate it around a equals 16, or if you want to think of it this way, I know that the point 16.4 would be on the graph of f, right? So I think that's my point. That's my point of use. But yeah, then if for some reason you can calculate the square root of 16.5 in your head, you can't. Then we could just get away with that. But we know something. We know how the square root behaves at like certain really well chosen points. 16.5 is not one of those places. So I'm going to linearize this to get a better idea. So I want to linearize f. How do I do that? Garrett, go ahead. Okay, what is the derivative of? Probably a good idea to do a rewrite if this one hasn't gotten memorized yet. So I got 1/2 radical x, and I want to linearize this around x equals 16. So my slope should be 1/8. All right, so I got the slope. What else do I need to do? Okay.
On the y-intercept.
Need to find the y-intercept. This time it's not quite given to me. So y equals mx plus b. I know an xy point. 4 equals 1/8 of 16 plus b. I think that means b is equal to 2. So my linearization is this: y equals 1/8 of x plus 2. We good there? So now, what can I use this straight line equation to do? So now I can approximate the square root of 16.5. That'll be equal to 1/8 of 16.5 plus 2, which is, so 1/2 by 8, that's like 4 and 1/16, which I think is equal to, I think that's, if someone correct me, okay. So that's the approximation of radical 16.5. And if we compare that to what your calculator says radical 16.5 is, what's that? 4.062. Give me one more decimal place.
0.
Oh, really? Okay. So again, as long as you're within the vicinity, I mean, it's accurate to not quite 3 decimal places, pretty close.
So I know the linearization, like concept of linearization, just like tangent line and then stuff in the value.
Yeah, I mean, the tangent line thing that we use derivatives for is not like an arbitrary random thing. We do it because the whole point of a tangent line is to kind of approximate the behavior of a function at a certain place. I mean, a line is a really, really simple thing. So if you're going to approximate something a lot more complicated, it's going to be a bad approximation for the most part. But you can approximate it around a single point. Any questions here? Okay. So let's talk about something called a differential. So far we've kind of talked about rates as, you know, these one unitized thing. Like, think back to we were talking about related rates on Monday, you know, dy dx, dv dt, all those things are like that. A rate is like this collective thing. But you can really think of those things as separate from each other. So typically we think of dy dx. And I'll go ahead and ask you, if I write down something like in that notation, what does dy dx mean?
Y with respect to x.
Yeah, it's the rate of change of y with respect to x, right? So up until now, we haven't talked about those things unless we haven't talked about dy unless it's in the context of dx as well, right? But we can talk about those things independent of each other. So we can think of dx as some independent variable. So some change in x. And then there will be a corresponding change of y, but I can deal with them separately. And just to show how these two things kind of go hand in hand, we typically say dy dx is equal to f prime of x, right? So the rate of change of y with respect to x is f prime of x, right? This right here kind of contains all the same information, except I'm saying the change in y comes from whatever the rate of change of y with respect to x is times some small change in x. So I have all the same information, representing it differently. Any questions on this thing before we move on? Again, it might be a little mysterious until we use it for some stuff, but the big idea here is I'm taking derivatives apart, essentially. Looking at their constituent parts. We've talked a lot about tangent and secant lines in the past. So in black, we have some nonlinear curve. In blue, we have, yeah, what's in blue? The tangent line, right? What is tangent to the curve where? At P, right? So there are two things we're looking at here. There's this idea of the differentials, dx and dy, and there are these other things called delta x, delta y. So basically what this delta x is, or dx, is the same thing here. Think back, we've just did a couple of linear approximation examples. That dx or that delta x is how far am I allowing myself to stray away from, in this case, P, the place where I am setting up this linear approximation. So kind of whatever you set that like kind of allowable tolerated distance to be, that's kind of your neighborhood around your point. Now these two things for x are the same, but for y they're different. Delta y is what the actual change in the function is. And dy, how am I calculating the dy here?
Between points R and S.
Right, so let's back up then. How do I figure out what S and R are? Like how are they related to the curve, the line, anything up here?
S is the endpoint of dx, x plus delta x.
Right, so S is basically the right end of this little interval right here. How do I calculate Q and how do I calculate R? Or I guess, Gary?
Q is putting x plus delta x into the function.
Right. So Q comes from the function itself, right? And by contrast, where does R come from? Okay.
The derivative.
Comes from the derivative, R comes from the straight line, right? So, there's only one point here, right? Because this is where I did my linearization around. But once you get away from that point, then you're introducing error, right? Q is what the actual function is calculated at. R is coming from your approximation, which is probably simpler, but it definitely introduces some kind of an error. So linear approximation, differentials, that's how these things go hand in hand with each other. If I'm trying to talk about some change in y, I have to have some corresponding change of x that governs it. So let's find that differential dy that comes from this function here. Really got to get started by doing this. I mean, I think we're a lot more comfortable at this stage in finding this thing, right? What is dy dx? More importantly, how do I get it? Chain rule, what are you doing with chain rule? Okay, it's good. That's what I was getting after. We want the derivative, right? So I want the derivative of f. Yes, I need the chain rule. So I'll erase this for now. So if I want to set this up using the chain rule, which I think you have to, I'll set this up as composite functions. Is two functions enough? Yep. If I set it up as g composed with h, then what are g of x and h of x? Okay. We just did this derivative. What's h prime? 2x, okay. Then based on that, let's do the full derivative of f, which is
1/2 root x squared plus 1.
okay. So this would be, so this is the derivative of g, the outside function, but it still contains the inside function h multiplied by
2x.
2x, which just simplifies down to x over x squared plus 1. So this whole thing is equal to dy dx, right? Almost there. How do I, so what did I ask for?
If you want to.
So how do I find differential dy?
Times delta.
I mean, there's no delta in there now. I don't need delta. So let me ask this question just fundamentally. dy dx, how many variables are represented here? 2? Could be 2, right? And up until now, we've thought about this thing as how many variables? Just 1, right? I mean, it's this single rate that joins y and x together, right? But basically differentials, it's this new paradigm that allows us to think of these things as being separate. So I really want dy. So how do I get dy? Yeah, multiply through by dx and you get x over radical x squared plus 1 dx. So dy will give me some small change in y, which is based on whatever value of x I care about and whatever small change in x. Like how you're going to deviate from that.
You just leave it like that.
That's what dy is.
Oh, okay.
Yeah, that's, I mean, well, what else would you like to do that?
No, I'm not yet.
Okay, so yeah, I mean,
Sure.
so, and let me just kind of back up. If I asked you to find what dy dx was, I think you would find a derivative of that and be totally satisfied, you could walk away from it, right? So, yes, dy dx is this derivative. This right here is the rate of change of the function f of x with respect to x. This right here is, this is how I find small changes in y as a function of x and some small change in x. Any questions there? Okay. How about this one? So I want to find dw. What should I do first? Okay. If I take a derivative of this, what would I call that derivative? What's a good logical name for it? dw dx, right? Actually, do we want to jump straight into this derivative, or should we break it down in a couple of ways?
Changeable, we're going to be down to x to the power 15 and then cosine 2x.
Did you ask me the product rule?
So product rule, chain rule, do we need both?
There's one.
Product will be equal. Don't you need both?
I think you need both.
Yeah.
Well, let's see. Those of you who are saying maybe you only need one, which one are you abandoning? Or maybe we should have to say it this way, which one do we absolutely need?
Product rule.
Okay, so let's start there. If we need something else, then we'll introduce it. So let's say what w of x is equal to a of x times b of x. And if that's true, what are a of x and b of x? Okay, which makes b of x
Cosine
cosine
to it.
2x. What is a prime of x?
15x 14.
15x to the power of 14. What's b prime of x?
Sine 2x.
That's part of it, that's not all of it. So this is, whether or not you actually like break it apart, this is a chain rule application here. So let's go back to my block diagram. We're just looking at b. If we're looking at the way b is defined, what's the first thing that happens to x?
You multiply by 22.
Okay, doubles. What comes out is 2x. What happens to 2x?
Cosine.
I take the cosine of it. So I really do have a function nested inside a second function, right? And we take a derivative going outside in. What's the derivative of this function, this cosine function? So that's going to be negative sine. But what's the input to the cosine function? 2x. And I multiply that by that other function which doubles things. Not 2x because it's
I'll just
just 2, right? So yeah, that first box right here, I would say this function is called 2x. And I would say this function is called cosine x. But yeah, take the derivative of those functions, you get negative sine of x, and then just 2. So yeah, the derivative contains negative sine of 2x, but if you stop there, you miss the inner function and then dealing with that. So b prime is negative 2 sine of 2x. And now I think we have everything, which means I can write down what dw dx is, or you can tell me what it is. What is the dw dx?
x to 14 cosine 2x minus 2x to 15 sine 2x.
All right, we happy with that? So close.
Is it plus 2x 15?
The product rule, yes, you add.
It has negative.
There you go. Yep. So the product rule, yes, you do add the two products together, but one of them ended up being negative. All right, so what am I actually trying to look for here?
dw
dw. So how do I arrive that there?
times the sine of gx.
Yep. Any questions here? What's the difference between doing this and finding derivatives the way we've been doing the last week or two?
It's just an extra step.
That's basically it, right? I mean, so far we haven't done much with it. So let's bring in an idea like, what does this dx idea really mean? What is, we talk about that as being some small change in x, but how do we, like, what does that look like if we're actually going to use it? So, like with everything we've done, when you're using local linearization, you are introducing error into a situation. So now we can quantify that error and give a name to it. So when you measure something, I'm guessing most of you in here are currently taking lab science classes or will need to at some point. You're going to introduce error into every single thing you measure. And you gotta try to quantify it somehow. So there's gonna be something you measure, in which, you know, in a perfect world, that would be your Q. But, you know, graduated cylinder, a ruler, a scale, all those things are inaccurate to some degree. That's like your delta Q. That's what that's the error you're subjected to. That delta Q is like a pure error, right? I'm off by 2 grams. Well, maybe that doesn't matter. It all depends on how big the thing is that you're actually measuring. And that's where this idea of relative error comes from. How big is this error as a ratio of the thing that I actually think I'm measuring? If you're off by a centimeter, are you measuring someone's height or are you measuring a mountain? You know, one of those is going to be a lot more significant than the other. You can also express it as a percentage error. So the relative error typically comes out to be some decimal quantity. Those can be translated to percentages, which is something that you'll have to do. So let's look at one here. I'm measuring a ball bearing. So I'm measuring the radius of a ball bearing, which I believe to be 0.7 inches. But I could be off by as much as 100th of an inch, 0.01 inches. What's the maximum error and percentage error in measuring the volume? So it's hard to measure the volume of a thing other than filling something up with water and tossing it in there. So I'm going to try to make that measurement based on what I can easily measure, which is the radius. So how is the volume of this thing related to its radius? Or are they related? What's the shape of this ball bearing? Sphere, right? Do we know how to find the volume of a sphere? We did on Monday. I think this is the most forgotten geometric formula. Yeah. So I will say this. Volume as a function of radius is equal to 4/3 pi r cubed, right? And what I want to do is I want to try to figure out I want to find out the error of the volume is. So what I am looking for, I'm looking for a small change in volume, right? Hopefully it's small. And based on what we've been talking about, the linearization differentials, what's a name I can give to that change in volume? Not a rate of change of volume with respect to radius. I just care about the change in volume. Not delta V, dV. I mean, believe that diagram I showed you, delta V was delta V came from like the linearization, right? We're going to get this measurement directly from the function itself. So what I want to find is dV. And I think I should stop here to make sure we're okay with why all these words clue me into the fact that dV is what I want. Any questions there?
So you're saying the dV we're going to get from the original function, not the derivative?
Yes, from the derivative, but I'm not gonna like linearize this.
Okay, so you're not going to do the tangent line.
No. I'm just going to get that here from the differential. Good question. So yeah, dV, because what can I underline that will
Error?
error is part of it.
Oh, the volume?
Yeah, I'm looking for the error in measuring the volume, right? I mean, I already know what the error is in measuring the radius. I already gave that away. So, but I want to know, the volume depends on the radius. So if I have an error in the radius, how is that going to filter down into how I calculate the volume? So I have a function here for how I find the volume if I know the radius. How can I get to dV from there? I need the derivative, right? If I find the derivative of that function, what will I have to call it? dv/dr. The function is v. It is defined in terms of r. So I will find the derivative and it will be 4 pi r squared.
Just saying dv is just saying the rate of change.
It is not a rate. So dv on its own is a change in volume. In this case, we're thinking about it as an error, but here's the thing. So the radius is 0.7 inches, right? As far as we know, we can find the volume based on that, right? That would be like our, in the language of the last slide, that would be like our Q. Because that's we call it the nominal volume. In a perfect world where I can measure things, absolutely, that would be the volume. In an imperfect world, our volume could be off by something. That's what this is. So that's one thing we haven't talked about. This is so let's represent this in terms of dv. So dv is equal to 4 pi r squared dr. If I told you dv is a small change in volume, then what does dr stand for?
Small change in values.
Right, and in this case,
That would be 0.01.
that's 0.01 because that's, I'm telling you, I believe my radius is this. It could be within 0.01 of that.
So you could input 0.7 for R and you.
Right.
And 0.01 for Q.
And that's exactly what I'm gonna do. So my change in volume is gonna be this, 4 pi constants. I believe my radius is 0.7 inches. Could be off by as much as 0.01 inches. And that gives me a 0.49 times 4 times pi. I got 0.0616. Unless someone disagrees with me, I think pretty sure that's right. .0616 inches cubed, which doesn't seem like a lot, but we should probably compare it to what the volume actually is. So for now, I'll say this, the dV is 0.0616 cubic inches. And just to kind of as an example, I think a lot of you are electrical engineering majors, or will have to take an electrical engineering lab if you haven't already. Resistors always say like they're 1,000 ohms or 2,000 ohms, whatever, they never are. So there's always some kind of error that they bake into them, which is why you have to measure it. It's probably gonna be like 980 or something. So yeah, and this is just anything that is measured, it could be off. So you just have to. You have to have basically this range for how good the measurements are. Any question about how we found this small change in volume? This possible, basically that is the worst I could be off in terms of volume. Because
in either direction, right? Small.
in either direction, yeah. Yeah, I mean that's one thing when I say this is just like an absolute quantity. I could be high by that amount or low by that amount in the volume. All right. So to figure out the relative error, we should probably figure out how big the ball bearing is, if we can measure it exactly. So we'll say this. The volume is equal to 4/3 times pi times 0.7 cubed. This right here will be a nominal measurement. .437 inches cubed, which means my percent error is going to come from this, the relative error, which is 0.0616 inches cubed over 1.437 inches cubed times 100%. .29%. I'll stop right there if everybody has any questions or any rebuttals on my terrible thumb calculator.
So DV in this case is the maximum acceptable percent error.
No, so I have not deemed what's acceptable. That DV is the maximum possible error.
Okay.
So I'm measuring the length of something with some kind of tool, and whoever manufactures this tool guarantees it to this accuracy. To measure, so the radius could, so I'm telling you the radius, I measured the radius to be 0.7 inches. It could be 0.69 inches, it could be 0.71 inches, or anything in between. Because that's as much certainty as I can give you about this measurement. But
And then the relative error without percentage would be 0.0429.
correct, yeah.
This is an equation thing. So for the 0.616 inches cubed over the 1.437, it's
Yeah.
the possible error over what? Like what's the?
So that's a good question. So this right here, and this is not so much a thing you'll see in your book, but like in a lab setting, you hear this called the nominal value. This is the volume that I believe it is, assuming there's no error in my calculation. But now what I'm telling you is this. I measured this volume to be 1.437 cubic inches. Really what the volume is it's 1.437 cubic inches plus or minus 0.0616 cubic inches. So basically, like bringing it back to differentials, the differential that we started with, the one we know could exist, is kind of a worst case scenario for the radius. But since the volume is based on that whatever error exists in the radius is going to have some kind of effect on the total volume.
And the 0.06 is the equivalent of the radius error.
What's that?
So the 0.0616 is the equivalent error for volume based on the.
I don't want to say equivalent, I'll say resulting.
Okay.
Yeah. And then that comes from this relationship here, or either one of these. Anything else? Do I have one more? I have one more. It's very, very similar to the one we just did. I'll save it for next time rather than just skipping it. So I have 319. I don't want to start this last example in just a few seconds, but almost done with section 2.8. So we'll start 3.1 next time.
So this might be stupid, but what does this derivative of dV stand for?
So volume is a function of radius, right?
Yeah.
Hold on.